Good morning, everybody. My name is Kostas. I'll talk about how much privacy we can get for free in the context of federated learning with secure aggregation. There are a bunch of co-authors. Most of the work was done by 2 students who, because of visa issues, etc., are not here, so I'm here to present. Quick intro to federated learning. It's a distributed way to train a model. The idea is that you're going to have your local models, each user, and then you're going to aggregate them together at the server. So basically, let's say that there are some gradients x1t at user 1. Eventually, you're going to just add up all the gradients if you're doing SGD, for example, at the server and get a global model. There is some kind of limited notion of privacy inherent into this because essentially you don't share your data. You share your model parameters. But of course, this is not that private. You can do, for example, model inversion attacks. They have been shown to be quite successful in this case. To deal with these, early on, people said, OK, why don't we do secure aggregation instead? So basically, instead of sharing your gradient update, you share a cryptographic obfuscated version of this. And the key here is that when you do this, number one, you are guaranteed correctness. So basically, the sum you're going to get is correct. And number two, if you are actually observing the obfuscated shared versions of your gradient updates, you can't really guess what are the actual gradient updates. So this solves this type of attack, but there are other attacks. Perhaps the most important of those is when the server, who is the attacker here, is exploiting the fact that he's getting multiple updates over time. So you can always ask the question, this is what the model was right before. I'm getting a new update. I can compute the difference. What might have been the data that have caused that difference? And this is the focus of that talk. So I'm going to quickly show you some analytical results. Then I'm going to turn into data sets and some experimental results. I'm going to briefly talk about differential privacy in the end. So let me start with the analytical results. And well, first we need to discuss or decide what is a privacy metric in the context of this talk. There's a lot of debate with that stuff. There are 2 basic privacy metrics, mutual information and differential privacy. This talk, well, if you don't know about these 2 metrics, 12 minutes are not enough for me to explain to you. But one thing you need to know for the rest of the talk is there's a key difference. Mutual information is an average metric. Essentially, those of you that know information theory or probability, there is an expectation up there at the top right. Whereas differential privacy is really a worst case metric. What this means is that with mutual information, there is a guarantee that there will be no leakage for most of the cases. But there could be a few cases that things may go wrong. But so few, the probability is really small. Differential privacy pretty much says, no, there is not going to be any leakage with high probability for no scenario, no case. That's a thing to keep in mind. OK. So what do we do? Again, the threat model is that the server is the bad guy here. You don't want to share your data. We will use, in this talk, mutual information as the privacy metric. So essentially, we are saying, if you know the aggregate model, the sum of XITs, and you also know the previous aggregate models on previous times, t-1, etc., what is the information leakage with respect to a gradient update of a certain user, user I in this case? The key intuition is that all the other users' updates could act or could be seen as acting like noise with respect to that user, and let's see how good this is. And technically, the analytical part, at least, we are trying to derive upper bounds. We are using some versions of central limit theory. Obviously, we don't have time to go through proofs here, so I'm going to only show you this slide when it comes to formulas. There are 2 bounds there. The top bound is for single round leakage. The bottom bound is for multi-round leakage. The only difference is the number of rounds t. So let's focus on the top right bound. There are a bunch of parameters. What are the important parameters? N is the number of users. B is the batch size. Everybody knows machine learning, understands batch size. D star, OK. D is the model size. D star is the rank. I'm going to get a bit technical here of the covariance matrix of the aggregates, which for large models is not really the same with the dimension of the model, but it is clearly related. Anything else? No, that's it. So what are the takeaways from this bound? Number one, you can see them here at the bottom. As you increase the number of users, leakage goes down almost linearly. You increase the batch size, leakage goes down almost linearly. You have a larger model, there is more leakage. You have more rounds, there is more leakage linearly. This is high-level takeaway model, takeaway lessons from the analysis. Now let's see if this thing actually checks out in practice. So we have a bunch of data sets with both IID and non-IID data. That's important. For the proof of the bounds, we have assumed IID. We are going to check the level of leakage over various parameters. First slide here with results is about leakage as a function of the number of users. Just focus on the top left plot. There are too many plots here. X-axis number of users, Y-axis normalized mutual information. If you want to ask me offline what I mean by normalized, I'll be happy to tell you. The key here is that you increase the number of users. After some initial curved stuff, you go linearly down, as you can see, for a bunch of different models, all the way from linear models to CNNs. And this is true for various versions of federated learning. The analysis, meaning the bounds, are for SCD, for the standard vanilla federated learning. Next is leakage as a function of the model size. Again, what we found on the bound checks, meaning as you increase, look at the blue arrow, the model size, you do get more leakage, meaning less privacy. Next is leakage as a function of the batch size. We are increasing batch sizes. You see the blue arrow going down now. As you're going down, you're getting less and less and less leakage. Again, in agreement with the model. Next is dependence on training rounds. This is not that surprisingly. Basically, the x-axis now is the number of training rounds. The y-axis is, as always, the leakage. The higher, the more the leakage. The lower, the less. And yeah, with more rounds, you are going to basically leak more data and lose more privacy. So far, everything works as expected. An interesting point is there is always a privacy accuracy trade-off. By the way, this is the case here, too. The more the rounds, the more accurate you're going to get, but you're going to leak more information. And that's indeed the case here, where I'm plotting on the y-axis leakage and on the x-axis model accuracy as the rounds keep on increasing. Now, looking at this, a reasonable person is going to say, yeah, OK, I'm going to basically stop training the model when I have enough accuracy, and I'm going to start losing a lot of privacy for no good reason. We are on this slide, maybe that's actually an important slide. We are dropping the IID assumption. So I'm reminding you that for the bounds that I show you, we have assumed IID because we use central limit theory versions. But actually, it doesn't really matter in practice, which is actually interesting. We have intuitive reasons about this on the paper. You can see the exact same pattern. You have here the leakage as a function of the number of users. And the good thing is the leakage goes down quite fast, actually. You don't need too many users. Last experimental results. If you don't really like models and formulas and that stuff, and you are wondering, OK, what does this mean in practice? Here we are actually staging an actual gradient inversion attack on a pretty standard model that it's trying to figure out what number and image is showing. And what I'm showing you here is that with merely 20-something users, you can't really stage the model inversion attack, meaning you cannot figure out that that was a number 3 on the image, just merely because you're aggregating 20+ users. So as you're just running the model, all the other users are protecting, as I said, the user under attack. OK, so last part. OK, great, but we have used really mutual information as our metric. What about differential privacy? Can we give any differential privacy guarantees? Well, the short answer is no. But let me tell you what's going on. Think of the main difference between the two metrics. If you have a few low probability scenarios where things break down, meaning there is privacy leakage with high probability, they are going to wash away when you are taking an average like mutual information. But if you want to guarantee for every single case that there is not going to be any leakage with high probability, well, then you are in trouble. And here's a counterexample. A very, very simple one. So let's say you have 4 users, and the 4th user, user 4, is under attack. And it just so happens, not very likely, but it so happens, that the first 3 users are such that on the last quarter of their elements, on their gradient updates, there's just a bunch of zeros. Then, in this case, the fourth user is not really protected with respect to the last 1/4 of their elements. So an X4 and an X4 prime are very easily distinguishable because there's no noise from the other guys, as you can see here on the right, and there is violation. So essentially, to guarantee the P, what you need to make sure is that the gradients of the other guys are going to cover all the dimensions of the gradient of the user that is under attack. And there are different ways to achieve this that I'm listing there, but I'm not going to get into that because this is not the focus of that talk. All I'm going to say is that, well, if there are some few dimensions that they are not covered, you could consider adding a little bit of noise, as opposed to just adding noise everywhere. Because if you add noise everywhere, you're going to have a bad accuracy. But maybe if you surgically add a little bit of noise, you're going to solve the problem. You still have good accuracy. OK? So takeaways. Interestingly, federated learning with secure aggregation, just thanks to the aggregation, will offer reasonable privacy against the type of attacks that we have discussed because the other guys are offering noise for the user under attack. And yeah, maybe you can argue, I could think of this intuitively. Yeah, but we have proved it, in addition to showing it with real-world data sets. But this does not mean that you actually have differential privacy guarantees. And there are cases, especially with large models, large DNN models, that they are ridiculously over-parameterized, where you do get a bunch of zeros in your gradients in some of the elements. So you may get in trouble. And, well, I guess that's it. Time for questions. And I have to say, I haven't used Tulip for questions before, so I have no idea how you're going to end up asking questions through Tulip. Okay, so can I take questions like that all the way? OK, go for it.
Thank you for the talk. My question is, when you consider the non-IID case, what is exactly your assumption of non-IID? How is it non-IID?
OK, good. So I'm going to go back to the specific data sets because that's the most precise way to discuss this. Are you aware of Feminist and Cypher 10 data sets? OK, so this is basically what you use. Feminist is non-IID by design. Cypher 10 has a parameter alpha, and as you are switching it, you make basically more, you increase correlation, think about it this way, between different data entries on the data set, and we have varied alpha. Alpha infinity is basically IID, but we have varied alpha. I'm going to find it somewhere. Where is it? Here. OK, all the way from 1, 1, 10, 100.
And C410 already has like 10% of the data.
OK.
Do you remove those and then apply non-IID transformation?
Can you repeat this?
Yes. C410 already has about 10% duplicated data. Do you take that out and then apply?
Yeah, when we are trying to do the IID, yes. So that we make sure that they are IID. Other questions, if we have time? Yep.
Yeah, so here, for me, it was for Anita, and I might have a mistake. What is the gradient accuracy? Because you're not using noise
You mean what is the reason?
Yeah.
OK, good. OK. Because when you're doing federated learning, you need a bunch of rounds because the global model has to converge. So think of this as you are, you have a bunch of users. Each user has different data that it's working with, but it's the same model, really. So by definition, the way federated learning works is basically an iterative process. So think of this as you are doing some, iterative optimization, essentially. So you do need a lot of rounds to converge, such that the global model converges to the model that you would have had if you were to sell all your data on a central server, and the server would just train the model with everything.
Thanks very much for the questions. Let's please thank the speaker again.